Good day, stats students. Today we're going to be talking about section 6.3, the binomial random variable. The reason why we're talking about 6.3 before we talk about 6.2 is that 6.3 and 6.1 go together. So if you remember, with 6.1 we were talking about discrete random variables. Well, 6.3 is a very specific discrete random variable, and so they go together. I'm not exactly sure why the authors have them separated, but they certainly go together, and so we're just going to continue our discussion here with discrete random variables and a very specific one, the binomial random variable. And then we'll get back to 6.2. So there are certain situations where we want to calculate the probability of some event, and it's relatively easy to calculate because the situation was run under very specific conditions. And so the very first time, we get this a lot in statistics, okay? And so the first instance that we run into this is with regards to the binomial, okay? Now, in order to have a binomial random variable produced, there are certain conditions that you have to basically run your trials with, and as long as you meet those conditions, then whatever x turns out to be will be binomial. Okay. Now you need all the conditions. You can't just have one or two of these present. You need all of them. Okay. And if you might only have one or two, you might have a completely different random variable on your hand. Okay. So you need all of them. So here are the conditions, and there's three of them, okay? And like I said, you need all of them. Now, as I read through them, they may not make a whole lot of sense right now. That's okay, because what I'm hoping is that they will make sense, okay? That once I give you an example, okay? So I'll give you an example. I'll say, okay, this is what this means, this is what that means, and so on and so forth, okay? So number one, there are n identical trials of which there are two possible outcomes. These outcomes are going to be either classified as either a success or a failure. Two, the probability of a success and a failure remain constant from trial to trial, and we're going to denote this as the probability of a success per one trial will be lowercase p. The probability of a failure per one trial would be 1 minus p. And so what does that mean? That means if you had a success rate of 90%, what's your failure rate? You know it's 10% because those things need to add up to 100% or 1. Okay. Three, the trials are independent. We'll talk more about that later on. Okay. And so if you have those three things, when x is produced, it will be binomial. And notice what x is. X is the number of successes. Number of. Sounds very discrete. You're either going to have 0 or 1 or 2 or 3 successes, and so on and so forth. Okay. And so let's go ahead and move on to the next slide. So here's an example, okay, of a situation that produced a binomial random variable. So example number one, we roll a six-sided die 16 times. What's the probability of getting exactly 7 odd numbers to be rolled? So let's start with the first one, the first condition. There are n identical trials of which there are two possible outcomes. Okay. So ask yourself when you do these problems in 6.3, what are we doing over and over and over again? Okay, clearly here what are we doing? We're rolling a die and observing either odd or even. Okay, and when you do that just once, that's a trial. Okay, so ask yourself, what are you doing over and over again? And when you do it once, that's a trial. Okay, and in the problem, what you got to find is the number of trials, which is our sample size here. Okay, and we've been calling our sample size throughout the semester n. So one of the things that you're going to have to do is identify n in the problem. Okay, so what are we doing here? We're rolling the die over and over again. How many times do we do that? 16 times. Okay, that means n is equal to 16. Okay, and notice we either had an even or an odd. Two possibilities. That's it. Okay, just two possible outcomes. All right. Next slide. Let's see, we will call these outcomes either a success or a failure. Let's talk about that. And what exactly does that mean? So a success is whatever the problem was asking about. Okay. So since the problem was asking about rolling an odd number, if an odd is rolled, okay, on any one trial, that would be a success, and an even would be a failure. However, if the problem stated what's the probability of rolling 7 evens, well, then rolling an even would be the success. Okay. So it's just how the problem was defined will define what a success is. Okay. Therefore, success is defined by the problem, and it doesn't have any kind of positive or negative connotation. So that means that doesn't mean anything good or bad. Okay, it it could, to us, something that is a success in the binomial could actually mean something kind of morbid in real life. So let me give you an example here. The last paragraph. For instance, if the problem asked, we test 100 people, what's the probability of finding 3 or more people with cancer? Well, since the problem was asking about people getting cancer, success would be finding a person, unfortunately, with what? With cancer. Okay. Obviously, this is not a very good situation, but in the binomial situation, this would be a success. Okay. So it's just how the problem is defined. All right, 2, the probability of a success and a failure remain constant from trial to trial. And we're going to denote this as lowercase p and 1 minus p. Okay. So the problem will either state outright, hey, this is the probability of a success. Now, a lot of times it'll do that, but sometimes we actually have to calculate it ourselves. And if we have to calculate ourselves, usually it's fairly simple and straightforward. Okay. And in our problem right now, that's the case. Okay, so let's think about this. You have a die. What's the probability of getting an odd number? Well, let's see. There's six numbers on a die, and you can either get a 1, 3, or 5 for an odd. So there's 3 possibilities out of 6. So it's a 50% chance of getting an odd. How about an even? 2, 4, 6. Still 50% chance, right? And so notice we had to calculate it, but it's really simple to calculate it, and there you go. Okay, and so the probability of success, 0.5, probability of failure, 1 minus 0.5, or again 0.5, right? So let's think about this. Is that going to change from trial to trial? So on roll number 1, there's a 50-50 chance of getting an odd. On the second roll, what is it? It's still a 50-50 chance, okay? And on the 16th roll, what is it? It's still a 50-50 chance, okay? And we want that. We need that constant probability all the way through all the trials, okay? So the probability of success and a failure are remaining constant from trial to trial, so we have that condition. Third one, the trials are independent. What does this mean? It means that whatever happened in the past won't affect the future. So for instance, if we rolled 15 evens in a row, which is pretty unlikely to happen, okay, but let's pretend it did. Does that mean an odd is guaranteed to show up on roll 16? Answer, no. It is still what? A 50-50 proposition, okay? And so to give you a real life situation of this, okay, casinos. So if you ever gone in a casino and you watch the roulette wheel, you played roulette, and what do they have there? They have those totes up that tells you exactly what came up in the last 10, 15, 20 rolls. And so you're taking a look at it, and let's say that you look at it and you go, oh, look, 7 reds just showed up in a row. The next one has to be black. Has to be. And so the casino's playing in your psyche. It doesn't have to be black. It's still what? It's still the same probability as it was before. Okay, 10,000 rolls beforehand. Whatever the probability was back then, well, it still is that now. Okay, and so our problems, we will simply state that the trials are independent. Okay, so we're just going to talk about it. There's nothing to prove. There's nothing necessarily to show. It's just something that we probably should talk about. Make sure that the trials are independent, and move on. Okay. So now, since we have all 3 of those conditions, we have a binomial experiment, which is going to produce a binomial random variable, and now we can solve for the probability that we get exactly 7 odd values in 16 rolls. Okay. So remember, x is equal to the number of successes. That means for this problem, x is what? X is going to be set to exactly 7. Get exactly 7 successes in 16 rolls. Okay. Therefore, we are trying to find the probability that x is equal to 7. Okay. Now, this is not easy to do by hand, so let me just show you. Yeah. Oh my goodness gracious. There it is. There's the binomial random variable formula. Okay. Pretty messy. Okay, as you can see. You may not even understand what some of that notation even is. Okay. That's okay. if you ran into this in the book, and or even if this is the first time you've ever seen it, it's fine, because we are not going to be using this formula. Off the table. Okay. So what are we going to do? Well, we're going to use tables to figure this out. Okay, and so as you just saw, figuring out all this stuff by hand would be tedious. Okay, so instead we will use a table that is simple to read, and here's a picture of a part of that table. Okay, and so I'm here at the bottom. It says here, notice that n is running down the side of the page. So here's n. Okay, and it's separated into pieces, parts here. We got n of 2, n of 3, n of 4, so on and so forth. Okay, and it goes on the table that the full table. You'll see that that goes all the way up to 20. At the top of the page, okay, you'll see things like 0.1, 0.2, 0.3, all the way up to 0.9. And what is that talking about? Okay, well, what that is, that's the probability of success p. And so what we would do is, let's say that we had n of 4. Okay, so we know that we're in this group of numbers. Okay, then we have the probability of success is equal to 0.8, and so that means we're working with this set of numbers. And what exactly is this? What this is a probability distribution. Remember in 6.1 we would give you a probability distribution when you would go ahead and just read the table. Well, that's what's going on here. That's a all these columns right here, all of these columns, this column right here, this column over here, this column right here, all of them, all the columns on the table are probability distribution, and our job is to find the specific one. So what we have to do in the problem is we have to find n, we have to find p, see where that comes together, find the correct probability distribution. Okay. So now let's focus in on what these probabilities mean right here. So I got them boxed in at with 0.002, 0.026, so on and so forth. Let's figure out what those mean. All right. So notice that x is right next to n. Okay. And so what all this means is this, is that let's say that n is equal to 4, so we had 4 trials. Okay. And what this means is that the probability that we get 0 successes when the success rate is 80% is 0.002, very small. Okay, probability of 1 success, 0.026, probability of 2 successes, 0.154, 3, 0.410, and 4 is also 0.410, believe it or not. Okay, and so that's the way you go about reading the table. What about for our problem? So we rolled a 6-sided die 16 times, with the probability of getting exactly 7 odd numbers to be rolled. Well, we already decided that n is equal to 16, so notice that n is equal to 16 here. Okay. P is equal to 0.5. P is equal to 0.5. Success is getting an odd, okay, and the probability that x is equal to 7. We have to go figure that out. Okay, so here's x 7. We come across, it looks like our probability is what, 0.175, and that's it. We go find the right probability distribution and we just read the table. Okay. So with regards to the binomial table, I want you to use this for solving all binomial problems involving probabilities. Okay, don't try to use the formula. Okay, that's 1. 2. Let's say that you have to you have signs like less than or less than or equal to, greater than or equal to, instead of just equal to. Well, that means you have to sum up those probabilities. Okay, so we're going to work an example here in a little bit that does that. This table you're going to be using for all homework and exams. So when you take your exam, you will get a copy of the full table. Okay, that goes where n is equal to 2 to 20. Okay, so whatever I'm providing to you, you're also going to get for the exam. Okay, table can be found in Brightspace under section 6.3. Maybe if you want to go ahead and pause this video right now, go to that 6.3 section, print out the table. That might be a good idea. Okay. And then this table does have limitations. What's the limitations? N goes from 2 to 20. Okay, can't have just one trial. You don't really have a binomial problem at that point. And so anything over 20, you would have to use technology. Also, the probability of success goes from 0.1, 0.2, 0.3, 0.4 up to 0.9. Okay, anything else? you would have to use technology. So if the success rate was 25% or the success rate was 75%, you would have to look someplace else, uh, you know, to figure that out. And by the way, you'll see that in lab, okay, where the success rate isn't point 0.1, point 0.2, point 0.3, or whatever. Okay, it's going to be something else, and you'll see how the technology works there. So here's another example. Okay, see if you can figure out what I want you to do is I want you to maybe get a piece of paper, pencil out, and see if you can figure out what a trial is here. Write it down. What is N? What is P? What is a success? What's a failure? What exactly X should be for these particular problems? Okay, so on and so forth. So it says here, example number 2, Roberto Alomar. So he was a baseball player. He played for Baltimore, the Indians. I think he played for the Blue Jays for a little while, and his career batting average is 300. So pretty good hitter. Okay, turned out to be just right around point 0.3. Okay, so what we're going to do is we're going to observe 10 of his career at bats. Okay, and see if you can read that problem and figure out, well, what is P, what is N, okay, what's a success, what's a failure, and so on and so forth. Okay, and then we'll go ahead and answer these questions A through F. Okay, so once you have figured all those things out, go ahead and go to the next page. So it says here a trial would be observing one of Roberto Alomar's career at bats and observing if he either got a hit or not. Okay, success, Alomar got a hit in one of those at bats, that would be a success. N is equal to what? 10, right? We looked at 10 of his at bats, that would be the number of samples. P is equal to 0.3, that was his batting average for his career. Okay, so this sounds very much like a binomial. And so if his career batting average was 0.3, that pretty much is probably pretty much going to be pretty stable throughout his career, I would guess. And then 2, the trials are independent of one another. And what does that mean? That by the time he got to the majors, probably not learning a whole lot. You can make an argument that maybe like a fourth grader, okay, who's just learning about baseball and stuff, that the more at bats he has, or for that matter she has, that person's learning, okay, and so the trials really aren't independent at that situation, okay, and the reason why is because the more you learn, the better that you're going to get, right? Well, by the time you get to the majors, okay, you're pretty much done your learning. I'm sure there's still, you learn about pitchers and stuff, but for the most part, we're just going to say that these things are independent. The trials are independent here. Okay. So I went ahead and produced the table. We have n is equal to 10, p is equal to 0.3. Okay. Here's our probability distribution that we're working with. All right. Hopefully you can find that in the table that you printed out. Okay. And then what is the probability he got exactly 4 hits? Well, that would be the probability that x is equal to 4. Okay. X is equal to 4. We come across, and it looks like 0.2. Okay. Simple as that. Go to the next one. B, I'm still down here. What's the probability he got 4 or less hits? Probability that x is less than or equal to 4. So we're going to include 4 here. Okay. We're going to include 4. So now don't skip over 0. There is people like to just put 0 for probability that you have 0 successes. No, there's a chance that he would have 0 successes. Okay, and so we have here 0.028, 0.121, 0.233, 0.267, 0.2, and what are we going to do with all those? We're going to add them all up, and I got a value of 0.849, just less than 85%. Okay. Next one, C. What's the probability he got less than 4? So less than 4 means, well, don't include 4. Okay, don't include 4, and so that would be what? 0, 1, 2, and 3. And we would go ahead and add those up. And so we got 0.028, 0.121, 0.233, 0.267. We add it up, and it comes out to just less than 65%, 0.649. Next, what's the probability he got more than 6 hits? More than 6 means what? 7, 8, 9, or 10. Well, we got to stop at 10. You can't have more than 10 successes. You can't have more successes than trials. Okay, so here we got 7, 8, 9, and 10. And we're just going to add those up. And so, as you can imagine, a baseball player, it's hard to get 7 hits in a row, 8 hits in a row, 9 hits in a row, 10 hits in a row. Okay, so it's a very small chance. It's only a 1% chance of that happening, 0.01. Now, notice for 9 and 10, we have 0.000. It doesn't mean that there's no probability there. It's just that the probability is so small, the 3 decimal places, it turned out to be 0.000. Okay, there is probability there, but it's really, really small. Okay. Next one was the probability he got 6 or more. He got 6 hits or more. So that would be the probability that x is greater than or equal to 6. Okay, so what are we going to do? We're going to include 6 now, right? So we got here 6. We got 0.037, 7, 0.009, 0.001, 0.000, 0.000. We added up. I got here 0.047. Finally, probability that x is between 3 and 7. We're not going to include 3, but we are going to include 7. So what are those numbers? 4, 5, 6, and 7. So we just go to our probability distribution. We look up probability that x is equal to 4. That's 0.200. 5, that's 0.103. 6, 0.037. 7, 0.009. We added up. I got here just less than 35%, 0.349. So hopefully that shows you how you would just add things up when you need to. Okay. All right, some tidbits about the binomial random variable. First thing, as long as we can boil the problem down to just 2 outcomes, it is possibly binomial. Okay, so that's one of binomial, bi meaning 2. That's kind of the distinguishing characteristic with regards to the binomial, that you want to look for something that has just 2 possible outcomes. Now, again, that's not the only thing that defines the binomial. Okay, but pretty good chance that it might be a binomial if you just have 2 outcomes. Okay, so what do I mean that we got to, as long as we can boil it down to just 2 outcomes? Let's say that, let me give you an example. Let's say that we want to know the, let's say the probability that a person the next person who's going to buy a car in the United States, he or she has plenty of options. Probably 40 different options, right? As far as probably even more than that, 50 different options. And so the person can buy a Toyota, can buy a Ford, buy GM, and all those different makes and models, and so on and so forth, right? And so we could say something like this: is that the probability that the person buys a Ford truck, okay, is 0.03. It's 3% chance of that happening. Okay. Well, what we can do is, if we can go ahead, if we wanted to, take everything else, take all the Toyotas, take all the GMs, take even all the other Ford cars and trucks and stuff, Ford cars and SUVs and all that other stuff, and kind of put them all together into one. And so you could say that buying a Ford truck, there's a certain probability, and not buying a Ford truck. Okay, and so you put all those other categories into that other one. And so if you can do that, you have yourself a binomial. Okay, we don't do that too often. Okay, but you could do that. Okay, the parameters of the binomial random variable are n and p, and every time n and p change, you get a different probability distribution. We saw that from the table. So every time, they're basically in control of the formula, and so since they're in control of the formula, every time they change, we get a different probability distribution that we have to work with. Those are considered the parameters of the binomial random variable. Next one, expected value, or the mean of the binomial random variable. So we found out in 6.1 there's a formula to figure out the mean of a discrete random variable. It's the summation of x times its corresponding probabilities. And you could use that for the binomial, because binomial is discrete. Okay, but let's say that n is equal to 20. You would have 21 things to multiply That's a lot of stuff to multiply. Well, what we find out is that there's a quick little shortcut formula that you can use. And all it is simply n times p, the number of trials that you have, times the success rate. And so just think of this as another still calculating the same thing. It's just that you have different information, okay? And there's a shortcut formula here, and we prefer the shortcut formula. And then the standard deviation of the binomial random variable is, so we'll call that sigma, and that's equal to the the square root of n times p times 1 minus p. Okay. Let me give you an example of those. So let's go back to our Roberto Alomar problem, and so we know that his batting average was 0.3 for his career. That's p. We're going to observe 10 of his career at bats. That's n. And we're going to calculate, let's say that calculate the expected number of hits, right? The mean number of hits by Alomar out of 10 at bats. Well, if his success rate is 0.3 and he has 10 at bats, we would take and just multiply those two together and get the mean. So that would be 10, right? 10 n times 0.3 p, and you get what? 3. Okay. So what does that mean? What does that indicate? Well, what that means is this, is that if we went ahead and looked at 10 of his at-bats and wrote down the number of hits that he had, and then we took a look at another 10 of his at-bats, wrote down the number of hits that he had, and so on and so forth. And sometimes he's going to get 0 hits, sometimes he's going to get 1 hit, sometimes he's going to get 2 hits, 3 hits, 4 hits, 5 hits. We just kept on doing this over and over and over again. If we averaged all possible combinations and stuff, and we just did this a whole bunch of times, you know what the average is going to turn out to be? It's going to turn out to be that 3 right there. Okay, so that's what that means. Now, just as a word of warning, sometimes students get a little confused about this. Remember, means, averages can take on decimals, and so if you calculate a mean to be 5.8, don't round it to 6. It's 5.8. Okay, leave it with the decimal. All right, even though the data was discrete, okay, doesn't mean that the mean, okay, does not mean that the mean has to be discrete upon its, also that can be a decimal. Calculate the standard deviation of hits. So we have n is 10, p is 0.3, 1 minus p is 0.7. We multiply all that together, we got the square root of 2.1, which turns out to be 1.45 hits. What does that indicate? Well, again, we do exactly the same thing. Sometimes you're going to get 0 hits, sometimes 1, sometimes 2, sometimes 3, sometimes 4. We do this over and over and over again, a bunch of times, right? And we calculate the standard deviation on those numbers. What does it turn out to be? Well, it's going to turn out to be 1.45 for the standard deviation. Okay, and so that's what that means. Okay, so I guarantee you that you'll get a question on the test with regards to calculate the expected value or the mean, the binomial, and calculate the standard deviation. Okay, so that takes us to the end of our presentation for 6.3. Please read the commentary, and I give you more different examples and more examples with regards to binomial. If you got any questions, please let me know. Thank you and have a good day.